Hey everyone, this is Fake News Labeling, a structured project part of Edna ML. My name is Asim Baral, and me and my partner Sukesh Talapati worked on this project. Now, just a quick introduction. The increase in fake news and false information has led to a lot of confusion and mistrust. This was especially prevalent during the pandemic, where the spread of fake news led to harm as people blindly follow health tips from people on the internet. To solve the existence of fake news, we could try to use machine learning to identify which news is fake, but currently the models are static and can't account for the constant change of fake news. As we are aware, the growth of misinformation is a major concern in today's society. The influence of misinformation sways people's opinion and action, so it's important to detect it in real time. However, existing machine learning classifiers are limited as they are trained on fixed datasets that are not updated, which means they're trained on the same data, but the fake news is always changing. That means we'd have to train on new fake news every time, which is just not efficient. Because it is so constantly changing and evolving, it makes it difficult for traditional classifiers to keep up. Our project aims to address this issue by scaling up misinformation detection for real-time with large volume streams. We're working with tweets collected from COVID-19 from January 2020 till now, group by month. Combining the labeled data from several months of data will allow us to detect misinformation in real time and capture the novelty of misinformation.
For our dataset, we're using the FNC or Fake News COVID Tweets dataset, and it's a collection of tweets that have been sampled related to COVID-19, and this collection has been happening since January 2020, and it's organized by month. So for our project, we're looking at August 2020 and September 2020 specifically, and each dataset is about 7.5 gigabytes. There are several features, including the information about the actual text of the tweet, the number of likes of the tweet, if the tweet was retweeted, and who actually made the tweet. So from these features, we extracted some of our own features, like the lengths of the tweet and the number of punctuation marks. The number of punctuation marks was pretty interesting to look at, since the majority of tweets had 6 punctuation characters, but a very small percentage had over 200. So this indicated to us that there's probably a lot of noise in our data set, and these tweets are not really relevant to us. Another interesting statistic I noticed is that over 70% of the tweets were retweets and not original tweets themselves. So that kind of tells us that most of this information in these months were recirculated and not original information. And for some of the features, I included some histograms. So on the left, we have the distribution of like counts. I did it with the percentiles rather than the raw counts, because the raw counts had a big spike at 0, and I couldn't tell much about the rest of the distribution. This shows us that even at the 97th percentile, the tweets had 0 likes, which means that most of the tweets had no interaction, and only a very small percentile of the tweets went viral and were seen by several users. On the right, we have the distribution of tweet lengths by percentile, and Twitter has a character count limitation of 280, and we see that most tweets were around a length of 150 characters, and the top percentile tweets were very close to the maximum limit, indicating that most of the tweets in the dataset were kind of medium length. Our overall goal is to build an extended tweet dataset that will be labeled in order to build and train a classifier for fake news detection. So to achieve this, our first step is to take the raw tweet data we're given for each month and filter it using COVID-19 keywords. The image shows the keywords that were used, and so tweets were organized into batches, and the batches that had the keywords were put into a filtered dataset, and tweets that did not have the keywords were put into an unfiltered dataset. Since we want to build a COVID-19 misinformation detection model, it's important that all the tweets we have are related to COVID-19 in some way. So for the September dataset, 2.5 million tweets were in filtered and 1 million were in unfiltered after the keyword matching. We can't ignore the tweets that were in unfiltered, because some of the tweets may still be related to COVID, but they might not explicitly have a keyword that was included here. There may also be intentional misspellings in the tweets with misinformation, and in order to avoid detection like this, and there may be other tweets that are still relevant to COVID that may not explicitly include the keyword. So we want to make sure we include these relevant tweets that were not caught in our initial keyword matching. So in order to do this, we trained a model on a masked version of the filtered dataset. So the filtered dataset includes tweets that have the keywords that we wanted, but if we mask the keyword and train a large language model on it, it will learn the context around the keywords. The BERT large language model processes each of the masked tweets in the filtered dataset bidirectionally to understand context before and after the masked keywords. By learning the context, we can identify if there are tweets with similar context to these in the unfiltered dataset, since those may be relevant as well. So in the training process, it's a little different since our goal is to minimize mask loss on several iterations rather than maximizing accuracy. This is because accuracy does not indicate whether the model understands the context around the masked words, so instead we're minimizing the loss. So for both the August and September datasets, we ran 2 training epochs with 56,000 steps in each, and the top screenshot shows the beginning of the first epoch, and the bottom screenshot shows the end of the second epoch. So if you see at the very beginning there's a mask loss of 9.9, and at the end of the second epoch there's a mask loss of 0.3. So there's a big difference there, but if you see the accuracy barely changes from the beginning to end. Since we trained the large language model on the mask filtered dataset, we now need to see how similar tweets in the unfiltered dataset are to tweets in the filtered data. So to determine the similarity and if there are any neighboring tweets in the unfiltered dataset, we can apply the trained large language model to the unfiltered data and cluster them with the filtered tweets. So before we cluster, we need to find out the optimal number of clusters, and to do this, we ran mini batch k-means clusterings with different clustering sizes from 10 to 100, and we plotted the inertias there. And if there are too few clusters, there'll be high inertia, and there's too many clusters, there'll be low inertia. And we plotted the inertias in the elbow plot, and we use it to determine the point of inflection, or where the elbow of the graph is, since that would be the optimal number of clusters. This graph here is for the August data set, and the point of inflection here would be 50, so it would be optimal to have 50 clusters here. And once we determine the optimal number of clusters, we use that number in the fast k-means algorithms to see which unfiltered tweets have high proximity in high density regions of the filtered data. These points would be considered neighbors to the filtered data, and they have relevant context related to COVID, but not explicitly the keyword, and they're added to the FNC neighbors dataset. In the end, we combine this neighbors dataset with the original filtered tweets to get the FNC extended dataset. And this dataset will be used to be labeled and for training for the classification model. We faced a lot of challenges throughout the semester with this project that kind of halted our progress. The first issue was with the Glamour library. We were unable to have certain dependencies, and when we tried to debug this ourselves, we were kind of limited with our knowledge, and we weren't able to access the source code to be able to understand it ourselves. Later on, one of the TAs was able to help us and gave us a fix for that, and this helped us to run the training initially. But Colab Free Tier had very limited resources, and we weren't able to progress past training much since we ran out of disk space. And every time the notebook crashed, all progress was lost. So we tried to scale down the dataset to resolve this. So we used 70% of the dataset, and we still ended up crashing, even though we got further along in the process. We tried as low as 40% of the data, and that still didn't even finish one epoch of training. And towards the end of the semester, we purchased Colab Pro, and this got us through 2 epochs of training, but we still faced issues with the Glamour library at the later steps that stopped us from fully finishing all the requirements we set out to finish at the beginning.
Well, one of our deliverables was supposed to be the 500 annotated samples, but the reason we don't have that is because the Colab notebook failed to run, and there was no real way to stop that issue from happening. So basically, we don't have that, but we have some other deliverables that we would like to show you. We have the data analysis and histograms for both months. This is just a notebook that we created ourselves to analyze the data. We have the January 2020 starter project that Abhijit gave to us, also in the form of a notebook. We also have both Colab notebooks for August and September 2020. We have the final report and the final video link. Here are some skills that we learned. Data engineering and trend recognition. We conducted data exploration and trend analysis by accessing the existing features, identifying new features, and understanding the distribution of features using percentile values and histograms. Now, with the evaluation of models, we learned that the importance of evaluating ML models properly and not treating them as black boxes. Interpreted the elbow plot to determine the optimal number of clusters to see where the data was most distributed. Writing and using using Python in Colab has been a valuable learning experience to understand just how cloud computing environments, resource allocations really works. We learned that the limited free tier resources aren't enough for our project. We had to invest in the premier free tier for like more data intensive operations. For AWS, we learned different things like how to set up kernels, notebooks, and S3 buckets. And though the documentation was difficult to understand, trial and error helped us navigate this platform and use the different services that it offers. We now use these skills for our personal projects and the industry. Another thing we learned is problem solving. Throughout this project, problem solving was really needed. There's always be problems that would always pop up and we wouldn't know what to do. And we realized the best way to do it was to take it step by step, sometimes do trial and error, and look for similar solutions that have been used in the past.